Okay, so welcome to the 24th video in the Discrete structures series, and this video is going to resume our last discussion about predicates and quantifiers. And as part of this video, we'll be looking at the predicate logic equivalences. Then we'll have a look at the process of negation of quantified statements. We'll then follow it up with a look at nested quantifiers. And this talks about how we can have one quantifier nested into the scope of another. So we'll see shortly. Moving on, we'll look at the order of quantifiers. And earlier in our discussion of propositions, we looked at how to translate English language sentences into propositions. So here we are going to do the same with predicates. So translation of English sentences to predicate logic. Okay, so that is the scope for today. And if you are unaware about the ideas of quantifiers, you need to go back and make sure you are aware with the quantifiers for all and their exist. And just for a very brief recap, this is called the universal quantifier and this is called the existential quantifier. The universal quantifier says that a property is true for all members in a certain domain, while the existential quantifier only says so for certain items in the domain. And we have already defined these and looked at a couple of examples in our last video. So we'll move on to our first topic, predicate logic equivalences. So as part of this topic, we're going to look at how the universal and existential quantifier distribute over conjunction and disjunction. So let me show you with an example. Consider this proposition: for all x, px and qx. So this statement suggests that for all members x in the domain, both px and qx is true. Therefore, in this case, I'm able to distribute this quantifier over the conjunction here. That means this will be equivalent to for all x px and for all x qx. Okay, so every student must be attentive and disciplined. And this one just distributed the every inside, right? So every student must be attentive and every student must be disciplined. So that makes sense. So let us make this even more clear by seeing why it wouldn't work if we were to use a disjunction. So for example, if I were to write for all x px or qx, this would not be equivalent to for all x px or for all x qx. So let us also see a relevant example. Let us assume that x is any time in day. My proposition px suggests that x is in am and qx suggests that x falls in pm. So now you could logically think and see that this is a true statement. For any time in day that I choose, it's either going to be AM or it's going to be PM. But what is this statement saying? Well, this says that no matter what time you choose, either all the times are going to be AM or all the times are going to be PM, which is not true. So we have our first rule here. When you have the universal quantifier or for all, you can distribute it over a conjunction, but you're not allowed to distribute it over a disjunction, as you can see here. And when we talk about the existential quantifier, it's just the opposite. So let me say there exists a x for which either of px or qx is true. Then from this I could successfully conclude this. Okay, so this is correct to say. And why is that? Again, let's see what this statement is suggesting. So it is just saying that there is at least one x for which either px is true or qx is true. And distributing it maintains the equivalence. Because ultimately for this statement to be true, some x must exist that will make px true or some x should exist that makes qx true. And this is referring to exactly the same fact. However, if I take a conjunction with an existential quantifier, let me write that down. In this case, it would not be equal to the distribution. So let me write that down as well. So it should also be easy to see why these are not equivalent. This is suggesting that there exists one x for which both p and q are true. But this one is talking about them separately. It does not preserve the property that the same x should make px and qx true. Here it is enough if some x makes px true and some other x makes qx true. Let's see an example as well. There exists a person that is rich and kind. So when you look at this expression, it means that the same person has these two attributes of being rich and kind. But this one simply says that there exists a rich person and there exists a kind person. It does not require the two people to be the same. Therefore, these are not logically equivalent. Therefore, when looking at predicate logic equivalences, those involve quantifiers, you should be aware of these two rules. The universal quantifier distributes over conjunction. The existential quantifier distributes over disjunction. The next topic that we're going to look at is going to be the negation of quantified statements. Okay, and this is going to be a really quick topic. We're going to look at what happens when you negate this expression for all x px and the existential version. There exists x px. So when I negate this, okay, so let's think about this. This one mentions that px is true for all values of x. Any x that doesn't satisfy this criteria will fall under the complement. Therefore, the negation of the universal quantifier is the existential quantifier and you are allowed to negate your proposition that lies inside. So we are saying that this is equivalent to there exists a x for which not px. And if this is confusing, look at this very easy example. Not every number is prime. And you can see why this is like this. And then what would be analogous to this one? Well, this is simply stating that there exists a number that is not prime. You see how this negation caused two things. It changed the universal quantification into an existential quantification, and then it also negated the value of the proposition. Similarly, you would be able to negate this one. What happens when you negate there exists x px? Because the original claim states that at least one x exists to make it true. In order to negate it, in order to prove this false, I'll need to prove it exhaustively for all values of x. Therefore, this would be logically equivalent to for all x, not px. And for an example to this, let's consider x is a car and px suggests that this car can fly. So this statement is saying there exists a car that can fly. For our discussion, we'll assume such a car doesn't exist. So the negation is the statement that we want. That is saying there doesn't exist a single car that can fly. Okay. And this one would be saying for every car in the world that you take, that car cannot fly. And you would be able to see why these two are the same. And the quick way to remember this is just that the negation changes the quantifier from universal to existential and vice versa. And then it also negates the proposition that is inside. And once we do that, the resulting proposition is also equivalent to the negation of the original quantified proposition. Okay, moving on to the idea of nested quantifiers. So the idea of having one quantifier within the scope of another is called nesting of quantifier. So let us see a few examples. For all x, there exists a y such that x plus y is equals to 0. So let us make sense of this. This one is suggesting that for all numbers x, and we are assuming x and y to be real numbers, and maybe it also works for complex numbers, but the idea is that for every given number x, I can find a y, okay? There exists a y, so that if I were to add that y to that x, the result would be 0. So we could choose any real number. Let's say if I choose minus 3.27, adding 3.27 will result to a 0. So we are saying that such a number exists for any chosen number. So you can see that the first number is chosen universally. It applies for all numbers, but the second number is chosen existentially because only one additive inverse will exist for that number. There will be only one y that can make x 0 when added. Let us see another one. For all x, for all y, x plus y is equals to y plus x. This should make sense. And see that I've used the universal quantifier in both cases because this will apply regardless of what values of x and y you choose. The sum of x and y will always be equal to y and x. But I hope you are able to see what happens if I make this into a for all. This will be an invalid statement because it's saying that any two numbers will add to 0, which is not true. Okay, let's look at third example, which is a little bit complicated. For all x, for all y, x greater than 0 and y greater than 0 implies xy greater than 0. So here we started universally. We started allowing any value for x and y, but then this implication has some restrictions. So we are suggesting that if x is greater than 0 and y is greater than 0, this means x and y are both positive, and that will imply that their product is also positive. But the main idea that I would like you guys to grab here is how we nest these quantifiers. Alright, let's move on to the order of quantifiers. And here we'll study for which quantifiers we are allowed to change the order and for which we are not. So let us also see a couple of examples. For all x, for all y, let's say pxy. So this is just like the example we recently looked at. For every x, for every y, this is true. Okay. In this case, if I were to change the rules for x and y, if I were to change the order of these quantifiers, would it be the same or a different statement? So I would just be writing for all y, for all x, pxy. And I can conclude that this is exactly the same as this proposition. The only difference is that this starts with one value of x and considers all values of y first, but this starts with one value of y and considers all values of x first. But whatever we do, we are going to find exactly the same permutations both way. It's just like doing 3 times 7 or 7 times 3. Well, not exactly, but you could find the analogy similarly. And the same thing goes for existential quantifiers. When I say there exists a x, there exists a y, and the proposition pxy, it would again be possible to exchange them. This is equivalent to there exists a y, there exists a x, pxy. Because the requirement in both of them is that some x must exist and some y must exist. It doesn't matter what order they exist in. And if this is confusing at all, we'll look at one example that combines the existential with the universal quantifier, and it should be extremely clear. So let's look at this expression. There exists a y for all x, qxy. And let me also write the other expression by flipping these two. So I'll write for all x, there exists a y such that qxy. And in this case, they will not be equivalent. And I can show you with an example. Let Qxy be this proposition. Okay, let's look at this one first because this is the correct proposition. This suggests that for all numbers x, you can find one number y such that x plus that number will be 0, right? Because this is the proposition. And you can easily see why this is true. For any x, you can always find a y. There exists at least one y so that the sum is 0. But why is this one false? Grammatically, it seems to be saying the same thing. There exists a y for all x such that x plus y is 0. But if you think really carefully, you'll find the difference. This is kind of saying that there exists a magic number y, and then once you choose that y, no matter what x you choose, the result is always going to be 0. Does such a magic number exist? Can you give me a really unique number y, and after you give me that number, no matter what x I choose, the sum will always be 0? Is that possible? Of course, that is not possible. Therefore, this is not equivalent to this. It is only true to say that for every chosen number, there exists some other number that will make it true. But it is absolutely false to say that there exists one such number for which for any other chosen number, the sum is 0. So I hope you can see the distinction and you can see how changing the quantifiers does make a difference if the quantifiers are different. So what is your answer to the question, does order of quantifiers matter? Well, if the same types of quantifiers are being used, it doesn't matter. But if they are of different types, they do matter. Okay, next we'll move on to the last topic of our video, translation of English sentences into predicate logic. We translated given English language sentences into propositional logic. Here we are going to do the same thing, but these are going to be sentences that involve quantifiers and predicates. So let me start with this example. Every student in this class has studied calculus. Okay, and the fact with these kind of statements is there's no single solution. I could write it in an overly simplistic way, or I could overcomplicate it to the greatest degree. So for example, I could call this entire thing P and be done. And we also discussed about this in our discussion of propositions. So P just represents the statement, every student in this class has studied calculus, and we're done. But you know that you won't get any marks if you do that. Let me write another possible answer to this. For every student x, Cx, okay? And Cx represents my proposition, x has studied calculus. And what is the domain of students for this quantifier? Well, it is all the students that belong in this class. But I don't think this should still be your answer. Let me show you this one. For every person in the world, okay? I'm not talking about the student, I'm talking about any general person. And I want to define two propositional functions. Let Sx represent x is a student in this class. And let Cx represent x has studied calculus. Therefore, I could write my proposition as for every person. If that person is a student of this class, that would imply that the student has read calculus. But be careful, you cannot write this Sx and Cx because this would mean that every person in the world is a student in our class and they have also studied calculus. Completely ridiculous. And so what is the right answer? Probably don't want to go with this one. I think this should be the good fit. I'm not saying that this should exactly be the answer, but something with this complexity should deserve being the right answer. Now, can I complicate it even more if I want? I absolutely can. I could start saying if there is an entity that is not an alien and living in Earth and a student in this class and so on. And for the course, I could consider calculus, science, physics, and I could build propositions that mention that X has studied a certain course and join that way. So it is really about you being able to judge what level of complexity is the best fit and making sure you don't leave your answer too simple or too overly complicated. Okay, so let's look at a couple of other examples. Okay, let's go with the same approach here. Let's consider the universe of discourse to be all students in the college or maybe all students in the world or all people in the world. Doesn't even matter. But I want to go one level higher than my statement suggests. So let's have Sx suggesting that X is a student in this class and Vx as X has visited Mexico. And I can see here some student. So existential quantifier, there exists a X such that Sx is true, X is a student in this class and Vx is true. Remember earlier with the universal quantifier, we didn't want to write the and because you remember if I change this sum to every, the proposition that I need to write is for all X, student in a X implies visiting Mexico. And it is just about meaning. If I put an and here, like we talked about earlier, we would be saying everybody is a student and everybody has visited Mexico. So this pattern might be really handy. In the existential sense, you will be using conjunctions, and in the universal sense, you will be using implications. But obviously do take my words with a grain of salt as there are no hard and fast rules here. Okay, we'll look into our last example that's really complicated and demonstrates a lot of ideas, including the ordering of quantifiers. So let me write this statement. There is a woman who has taken a flight on every airline in the world. So let's start by identifying the subjects. Let's call this woman W. Let's call a flight F and an airline as an A, because I see these are the three subjects or entities in my proposition. Now let's examine the nature of the quantification. There is a woman suggests that there exists a woman. It is not universally talking about all women, but simply suggesting that there is one woman. Okay, so we have existential in the woman. What do you think about the flight? Take on a flight. Is this about every flight in the world? No, it's about some specific flight. Because for that woman, some flight exists. So it's gonna be there exists a flight, and I'm writing these randomly because I don't know the order yet. We're gonna discuss in what order we're gonna write these. But let's move on. What about the airline? Well, it says every airline, right? So for every airline. Okay, now let's identify in which order we need to write these three things, because that is the most important here. So what happens if I write this? For every airline, there exists a woman. Is that what this sentence is saying? Is there a different woman for every airline? No, we're talking about the same woman that has taken a flight in every airline. Okay, so there exists a woman for which all airlines. And then I want to continue this way. So that helps me resolve the order of these two. And where do you think I need to put the flight? If I put it in middle of these two, I would be saying that the same flight exists for all airlines, because the all airlines part would come after the flight. And it is not the same flight for all airlines. It is rather the case that for all airlines, a unique flight exists, which this woman has traveled in. So my order of quantifiers is there exists a woman for all airlines and there exists a flight. So if this is not clear, please spend more time on this. You want to be absolutely sure why this order of quantifiers is being used here. Okay, and what is my proposition that involves W, A and F here? Well, I could just say one proposition. I could say P, W, A, F. Woman W has been in flight F of airline A. But in my personal opinion, I wouldn't do this. This is again too simple. Let us find at least two relationships. Let's say P, W, F as woman W has been in flight F. And then we can say Q, F, A as flight F belongs to airline A. And then now I can complete my statement. There exists a woman for every airline. For some flight, this woman has been in this flight and this flight belongs to this airline. So I could say PWF and QFA. And when you are doing this formally, please make sure that you describe your propositional functions correctly, and then you can go about writing your propositional statement. Alright, so that will be all the discussion for us to have today. I'll start next video with a look at the rules of inferences, instantiation and generalization. So I'll see you guys tomorrow with the next video. Until then, have a great day and bye.